I think today. You want this job? You can have this job. Okay, there truly is a cookout today, though, isn't there? That happens today, right? Okay, good. At C4C, bring your name tag. Wednesday. I don't care. I am free web.
Okay, good morning. Any questions about yesterday? I put some stuff on the wiki in response to questions after class. Okay, so we're going to start talking today about the perturbations around the cosmology. This is a little, it's more complicated than what we did yesterday, and I think it's a different way of thinking about data than particle physicists usually do. Instead of looking for signals, we're looking for the variance in a signal. In other words, we're not looking for, no theory predicts that over there in the sky we're going to see something. That's not interesting. What's interesting is the statistics. And so we have to, so really everything in cosmology now that's interesting is it has to do with statistics. So that's why it's, I'd like to walk through this a little bit slowly. Okay, so let's talk about first the statistics in real space. We're going to mostly be trying to probe the matter distribution in the universe. So we're going to define a quantity that depends on time. We'll call it delta and space. And that's defined to be the energy density in space as a function of time divided by the mean density, which depends only on time. So this is the fundamental quantity that we're interested in. And again, no theory makes a prediction that, we would live at this particular point in the universe. But theories make predictions for the distribution from which this quantity is drawn. Okay, so that's kind of a profound point that I'm going to spend a half hour elaborating on. Okay, so what do we know about this quantity? Well, we can immediately do a histogram based on what we know of what this looks like. So if this is delta of x, if we just looked at all the values of delta in rooms this size all through the universe, we'd get a distribution that looked like this. Well, the smallest delta can be is when the rho is 0, and then delta is just -1, right? And the largest delta can be, well, let's take this room as an example. The density here is 30 orders of magnitude larger than an average place in the universe. So it can go from -1 to 10 to the 30th. So that it's very sharply, it's a very weird distribution. And by definition, on average, since the average value of this thing over all space is rho bar, on average, delta is 0. Right? That means it has to be it's a skewed distribution. That looks like that. Right? So that's right off the bat, without knowing anything, you see we're dealing with something that's rather odd. All right, so what do we know about that? We'll use angular brackets to denote the average of the distribution. The average of some quantity averaged over all positions in space. So the average value of delta we know is 0. And that means we can't learn anything from the average. Just by definition, the average is 0. So the next thing, your intuition is the next thing that you'd like to look at is the variance, right? How much it's fluctuating from one point to another. So the fluctuations, so the variance, so that's an interesting quantity. We'll call that sigma squared. And that's defined to be the average value of delta squared of x. And I'm going to drop the time dependence, but there is a time dependence that we'll come back to. Okay, so that's an interesting quantity, but that's just one number. A slightly more interesting quantity is the correlation function. So the correlation function is defined as follows. You take the average value of delta at some position x, and you multiply it by delta at that position x plus a distance r away. And you average, and remember, again, these averages are always over x. So you sit here, you look at measure delta here, and then you measure delta, everywhere a vector r away. So this is defined to be the correlation function. So in principle, this depends on both, where you choose to put the center point x, and it also depends on how far away you choose to choose this vector r. Yeah, good point. So I have done that. Okay, good. So right, good point. Let's imagine that I want to make a point. That's why eventually this is going to go away. But I want to make a. Let me make the point and then come back to your question. The point I want to make is that it doesn't matter what x value you choose. That is, if we choose x to be here or anywhere in the universe, it doesn't matter. And why is that? Because we believe fundamentally that the properties of this distribution are the same everywhere throughout space. So that notion called homogeneity means there's no special place in the universe. That implies that this correlation function is a function only of the position r. Now you're right that the way if I define this to be an average over x, what I'm saying doesn't really make sense. So imagine thinking about it like this: doing this average at some big part in space and doing it in some other big part in space. It doesn't really matter. It's a different x. But you get the point, right? That it doesn't matter where you do this average. The only thing it should depend on, if we believe in the homogeneity of the universe, is it should only depend on this vector r, the distance between the 2 points at which we're taking the overdensities.
So x is more the center point of where you started.
Yeah, but again, by definition, the way I defined it, I'm going to do this at many different values of x to build up statistics. And the point is, if I do that, then it no longer depends on x. So it's, but you get the idea that at the end of the day, it's all moot because of homogeneity, it doesn't matter where you do it. You can do it anywhere.
You also integrate t? Or?
I'm leaving t as t. There's still a t dependence. It's implicit. I don't want to write it every single time.
Okay.
So this will turn out to depend on time, as we'll see.
Sure.
Other questions? Okay, so there's one.
Homogeneity, not the translation invariance.
I think it's the translation invariance is the. I think that's the same thing. Yeah. Yeah, that's right. But there's another symmetry, and that is, if I'm sitting here, and I look at the overdensity in every region in the sphere around me, it should be isotropic. It shouldn't matter whether I look in that direction or that direction. So it shouldn't depend on the direction of r. It should just depend on the magnitude of r. So isotropy, and you can imagine. In fact, people have imagined breaking this. But the simplest idea is that the universe is homogeneous and isotropic. In that case, the correlation function depends only on the distance r. Okay. So there's another way of defining this correlation function, and that is the following. They kind of follow from one another. A more physical way is saying if you look at the expected number of, let's imagine that galaxies exactly trace the matter, just for simplicity for a second. So the expected number of galaxies a distance r from, if you're sitting on a galaxy. So say, for example, if we're sitting on our galaxy. So I guess this is a heuristic definition, but it's useful. So that is equal to the mean number of galaxies, the mean density of galaxies, times the small volume that you look at if distance r away, right? If you take the volume to be infinitesimally small, you get 0, but you have to have some finite volume. So that would be if there's no structure in the universe, that would be the answer. You just take the density times the volume, right? So if there were, one galaxy per cubic megaparsec, and we were looking a megaparsec away, then this it wouldn't first of all, it wouldn't matter how far we were looking away. If it was only the mean thing, then the answer would just be 1 galaxy per cubic megaparsec, and let's say the delta V was a cubic megaparsec. We'd expect to find 1 galaxy in every region, right? There the universe is not homogeneous, and it's fundamentally homogeneous, but there. What I'm saying it's homogeneous, but now I'm saying it's inhomogeneous. What I mean by that? What I mean is I guess a more correct way to say it is that there is this translation invariance. It doesn't matter where you do it, the distribution of inhomogeneities is the same, right? I think that's a more accurate way to say it. And so there are definitely inhomogeneities. Witness this curve, right? However, the fundamental properties of those inhomogeneities don't vary from one position to another, right? So anyway, coming back to this heuristic definition, the number of galaxies that you expect to get is equal to this. So it's enhanced by this correlation function. And this kind of gets physically at what we understand a correlation function to be, right? If things are correlated, then if you're sitting over here, I'm more likely to find something nearby. Right? Does that make sense? And so this correlation function then is a very important measure of the properties of the galaxy distribution. So we can actually measure this correlation function. And, I don't want to get hung up on galaxies or what types of galaxies or anything like that. But roughly speaking, if you do this for almost any tracer, the magic number is 1. And roughly speaking, this correlation function is 1 at about 10 megaparsec. What is what? This is just if you imagine you're sitting in something, right, and I ask how many galaxies there are in a given pixel far away from me, I have to tell you the size of that pixel. If the pixel is 1 centimeter, there's not going to be a galaxy. Yeah. Okay, so anyway, so this correlation function turns out to be it has a kind of a weird, not a weird, but a semi-surprising shape. It falls off as basically r squared. So this gives you the sense that if you're looking very far away, the universe is pretty much random. That is, on large scales, if you smooth over large scales, and you ask how many galaxies there are, a very large distance away. Does everyone know what a megaparsec is? It's 3 times 10 to the 24th centimeters. So if you look far away, then you basically get the average number of things, which means if you average over spheres, say 30 megaparsec, you take spheres of 30 megaparsecs everywhere in the universe, you'll get the same amount of matter to a small error. That's useful information. Yeah. Okay, good question. It really can't be, right? Because you can't always have a greater than average probability, right? What is that? That's a Lake, whatever it's called, Lake Wobegon. So not everybody's over average. So at some point, the correlation function must go negative at very large distance in order to compensate. Good point. Good question. Yeah. Other questions? Order sounds like a technical term, though. What do you mean by order? Yeah, exactly. So, right. So if you would draw a random distribution of points, you'd get something like this, and so that's random. That's not what the distribution of matter in the universe looks like. Instead, it looks like this. Right? So that's the sense in which there's order. Right? And obviously, I kind of exaggerated it, but if you look in our galaxy maps, you can kind of almost see it by eye. There are these large clusters that are the centers of filaments, and in between there are huge voids. Now, another way of thinking about it is thinking about a population map of the United States. So, there's this dense regions on the East Coast, and the West Coast is large voids in Montana and stuff. So that's kind of a nice way of thinking about it. You can actually do the correlation function of the population, and it looks something like this in the United States, right? On small scales, it's large, because when New York is near Boston. But or if you have very small scales, if you go from 42nd Street to 100th Street in Manhattan, they're both very large over dense regions, right? And similarly, if you go in Montana, they're both very negative, right? So in that case, so the correlation function is on small scales is very large, and on large scales it's quite small. That is because you got like a positive and negative cancellation. Yeah. It would be what? No, because actually galaxy clusters themselves are are actually even more correlated than galaxies. That looks like this. The large, if each point was a structure, could I find a structure that looks completely random? Right. Good question. Okay, good. And I think we know the answer to that question. So if you took all the galaxies in a sphere of 100 megaparsecs, then by eye you wouldn't be able to tell the difference because C is so small. So then it would look like this. Good. That's good. Or not only galaxies, just all the matter, say, in a sphere of 100. Yeah. A cluster is like a megaparsec. Other questions? Yeah. Between galaxies? I mean, between this or between this? Okay. Right. So, yeah, you could tell that by that, right? So this characteristic distance is 10 megaparsecs or less, because that's you can see that by eye. This characteristic distance is the distance over which things are uncorrelated, which is roughly 100 megaparsecs. So that could be the size of voids, and therefore that's within a factor of 2 this distance as well. So we're looking at this is 1 to 10 megaparsecs, and again depending on what these dots are, and this is the big empty regions and the space, the distances between big stuff is hundreds of megaparsecs. No, I don't mean that. No, so right, no. So the mean distance between galaxies is about a megaparsec, but that's just that just has to do with the density and stuff like that. But yeah. Okay, other questions? Okay, so this is to build up our intuition about what the clustering statistics are, and that they're important. I'd like to now move to Fourier space, because that turns out to be the way it's easiest to analyze things. And given all this, we can now directly just use some math to translate these results into Fourier space. So let's do that. Yeah, sure. How does it behave? Well, okay, good. So that's a good question. I'm going to punt on that question and say that it's not interesting to us. It's very interesting to astronomers and people who are interested in galaxy formation, but we're physicists. Right? And why is it not interesting to us? Because the reason it's not interesting to us is because it's very hard to predict what that's going to be. Because once you get here, things become nonlinear, right? And similarly, things like the physics of baryons and black holes and everything become important, and supernova and galactic winds, and we just don't want to learn about that. So we could want to learn about it, but if we're interested in learning about the physics of neutrinos or dark energy, that's not the place to look. So what I just said is a little bit, in some quarters, is a controversial statement. Some people think the opposite. Some people think, let's just study what's close to us and learn about that, because how could we possibly hope to learn about this far stuff? So in some ways, what I'm saying is a controversial thing. It's surprising. It's different than anything we've ever done. Typically, what humanity has done is we've looked close to us and gone slowly further away. And there are still people who are doing that. Those people generally are people who believe in MOND, modified Newtonian dynamics. They say, let's look at stuff close to us, like galaxies very close to us, and let's understand that. We don't know anything about cosmology, right? That's the only reason the MOND industry still exists, because they basically ignore everything out here. So there's a complete philosophical shift between those people who are not crazy necessarily, and cosmologists who say, no, the reason why we want to look out here is because it's easiest to make predictions out here, right? So that it's really an important philosophical distinction. So your question's a very good one, and my answer is in here it's very, very complicated. So it's very dependent, for example, on what types of objects you're using as tracers. Other questions? Okay, so now let's switch to Fourier space. So we have to establish Fourier conventions. These will be mine. The Fourier transform of the density will be defined as the integral d3, I guess we're using x, times e to the minus I k dot x times delta of x. So that's the definition. So delta is nominally complex, but its mean, just like the mean of delta of x, is 0. So again, in order to learn something, we have to look at its correlation function. So let's consider delta twiddle of k. So I could multiply that by by the delta twiddle of k prime. That's perfectly fine, but it's slightly, that's what I usually do, but just to make things a little more intuitive, I'll use the complex conjugate here. So just jumping ahead, what we're going to see is the only time where this is non-zero is when k is equal to k prime. And that means that what this is really a measure of is the amplitude squared of these Fourier transform amplitudes. Okay? And so that's why I put in the complex conjugate. If I didn't do that, it wouldn't be the amplitude squared, so it wouldn't be so physical. It would still make perfect sense mathematically. It just wouldn't, it would just be this. So anyway, so let's just do it like this for simplicity. Okay. So we can do this now. Let's carry out this 2-point function. All right. So this is the integral d3x e to the minus I k dot x, and then it's the integral d3 x prime. I took the complex conjugate, so it's e to the I, e to the plus I k prime dot x prime. And then the expectation value is the expectation value of delta of x times delta of x prime. You agree? Well, we know what this is. This is just the correlation function, which depends only on the distance between x and x prime. Let's call that r. And in fact, since this depends only on one of these x's, one linear combination of these x's, let's change one of these dummy variables so it's on R. And that will mean the other integral will be free of anything. Okay? So let's change dummy variables. Change say the x prime integral to R is equal to x minus x prime. And that means that we replace x prime everywhere with x minus R. So then this integral is equal to the integral d3x e to the minus I k dot x e to the integral d3r, because d3x prime, same exact thing, and then e to the plus I k prime dotted into x prime, which is now x minus r, times the correlation function, which depends only on R. Okay, so now you see that there's an R dependence here, and that's going to be complicated, but the x integral is trivial, right? The x integral is just the integral d3x e to the minus I x dotted into k minus k prime. What's that equal to? Great, so you guys all know that. So that's equal to 2 pi cubed times the Dirac delta function of k minus k prime. Which means that this 2-point function in Fourier space is equal to is proportional to a delta function times what I'll call the power spectrum, where this power spectrum is just what's left. It's this R integral. So it's the integral d3r e to the minus I k dot r times c of r. And because the correlation function depends only on the magnitude of r, the amplitude of r, similarly, the power spectrum depends only on the amplitude of k. Right? That will turn out to be very important.
Yeah, I think it just becomes homogeneity and isotropy implies so you can do this the same thing.
Good. Yeah, I think translation invariance is a better word because homogeneity got me screwed up. So I think that's a better way to say it. I like that. Good. Thank you. Okay, so this is the result. Okay, I want to make 4 points on this. 1, 2, 3, 4. Okay, so the first point we've already made, that the power spectrum is a function only of k, and that is corresponds to let's call it translation invariance. And actually, this is going to be broken. There's a fascinating place where this is going to be broken, which you've already learned about. Do you know where it is? Good. Where? Why? That wasn't the thing I was thinking of, but yeah, I don't think that changes translation invariance. But but maybe it does. So I don't want to. When you ask a question, you're expecting the answer. Someone gives a different answer. Sometimes means you're not thinking broadly enough. So let's put your answer on hold. I think and it certainly leads us to what I wanted you to say, which is CMB lensing. How does that break translation invariance? Well, if you look at the power spectrum in this region of the sky, that is different than in that region of the sky. Why? Because the structure along this line of sight is different than the structure along this line of sight, right? So that means this is really the lensing properties here are different. they're modulated by the gravitational potential along the line of sight, right? So the fluctuations here are going to be modulated by this phi along this line of sight, and the fluctuations here are modulated by the phi along this line of sight. It means translation invariance is broken, and when that's crucially important. That enables us to determine the gravitational potential along these different lines of sight. And the way that plays itself out, I hope we'll get to it. And the fourth thing is that this statement is no longer true in the CMB. That only k equal k prime is good. Okay, good. So you've all walked me away from using fancy language. So let me stop doing that and stop using. Let me just try to say it. It's a good point. How about this? We've just proved that the fluctuations are only correlated when the two wave numbers are the same. Okay, I claim that if you have in the CMB, that's no longer true. Do you believe that? It's if you do the average in a given spot over here, take the power spectrum of the CMB in a 100 square degree region over here, and a 100 square degree region over here. That's not a global average, so that's a local average. So then those two estimates of the power spectrum will be different. That's right. So I'm redefining it, and we'll do that a little more quantitatively. I don't think Nalima did this. She didn't exactly explain. So let me promise to get to this, but keep this in the back of your mind that these two things the fluctuations are only correlated in this case when we assumed. Again, I don't know the fancy language, but I don't know what I assumed. But they're only non-zero if the two k's are the same. Yeah. No, that's not assuming non. I'm pretty sure that's not assuming Gaussianity. That's correct, but that doesn't show up in the 2-point function. It shows up in the 3 or the 4-point function. No. Okay. Sorry. Right. Good. So you're saying, are these two things correlated in a finite volume? Could you have? All right, let me think about that. Good question. I think those are two separate questions. If you talk about the non-Gaussianity, I completely agree that what that means is that if you estimate the power spectrum, things get complicated. There's mode coupling that leads to non-Gaussian contributions to the variance. But you're saying something stronger than that, even. That this simple estimate. Well, let's get to this estimate. Let's get to this estimate because you're way ahead. All right. So anyway, this is the first I thought simple thing. So now the second thing. Yeah. Yeah. Exactly. Good. Thank you. Jesus Christ.
So you have to compose homogeneity and isotropy. Now the lensing breaks x up by the potential effect. So what she was saying is just it's not fundamentally CFTs and isotropy. It's the lensing that breaks. Forget all that. Yeah. That's the point. Yeah. Yeah, you break isotropy. So
Yeah.
we talk about case-based.
So sorry, we have to be. I'm behind you guys, but you have to be a little bit careful when you talk about the CMB versus this, because here we're doing a 3D thing, there you're doing a 2D thing, right? So there's an analogy, but the isotropy there corresponds to the inhomogeneity here. So it's a little bit. We don't want to jump too far ahead to try to incorporate that. Okay, these are all good points. Let me try to get back to you with a more definitive explanation thing tomorrow. Okay, the second point speaks to. By the way, what's her name? Kaylee? Caitlin. All right, so what Caitlin said is that the spectrum, the estimator here is complicated. Let's talk a little bit about that estimator. So what does this mean? So this is what we're saying effectively is you take the Fourier transform of stuff, and you take in order to get the power spectrum, what you do is you take the amplitude squared of delta of k, right? And that gives you an estimator. But the thing that helps you enormously is that there are many different, there are many k modes with the same k. Right? There's ones that point in that direction, in that direction, in that direction, in that direction. So that's what really is tremendously useful. So you can imagine building up a histogram of delta twiddle of k squared, and just plot the number of them. You know, there's going to be tons and tons of them within a given dk shell. So this is what you were saying before. And so the more you have, so your histogram will look like this. Right? And this will give you a good estimate of an estimate of what this mean here is the power spectrum. Right? And clearly, if you have two modes, then you're not going to get a very good estimate of the power spectrum, right? If you just have two modes. If you have 4,000 modes, you get a much better histogram. You'll be able to get the mean of those values better. So in order to estimate the power spectrum, you have to take the Fourier transform, get lots of different modes with roughly the same k value, and then average them together to get an estimate of the power spectrum. That's one way to think about it. Okay. So with that in mind, it's clear then that your error on the power spectrum is going to depend on how many modes you have, right? So let's take the simplest example. The simplest example would be a Gaussian field. So with the Gaussian field, you can show that, remember, we're looking for essentially the variance of something. So you can show that the variance minus the true variance, if you, so you want the variance of the variance, right? That's the error on the power spectrum, right? So you can show that this is equal to twice the variance. Squared, I guess. Squared. Is there a square? I think that's right. Okay, so and what that corresponds to is that your error on the power spectrum is going to be equal to the square root of 2. And then, of course, the more modes you have, the better you do. So the number of modes you have in a given k region times the power spectrum. So this is for a Gaussian field. This is a simple formula, and the number of modes you have depends on, well, think about it. The larger k value you have, you get more modes, right? Just the density of states goes as k cubed. So the number of modes is k squared dk. It turns out there's a 2 pi squared, and then you multiply by the volume. So this is essentially the density of states times the volume. So that gives you the number of modes. So in other words, in order to measure the power spectrum well, what you want to do is you want to get a survey that has a large volume, and as Caitlin pointed out before, if you're looking at very low k, very large scales, you have very few modes. So you're going to likely have a very poor measurement of the power spectrum. Okay, does that make sense? Questions about that? Yeah. What is a Gaussian field? So in this case, this is a calculation that you should do. What I mean is you take something that has a distribution f of x is equal to 1 over the square root of 2 pi sigma squared e to the minus x squared over 2 sigma squared. So very simple. A Gaussian field with mean 0 and variance equal to sigma squared. So that's exactly what I mean. And I claim if you calculate this, you'll get this for a Gaussian field. Exactly. Okay, good. So the universe, as I pointed out, is very non-Gaussian. This room is very that thing. However, if you go to large scales, the field is pretty close to Gaussian, actually. So the density field that we've been talking about, right? So a reasonable approximation on large scales is that this delta, or in real space, goes as e to the minus delta over 2 sigma squared. So that if you smooth the field on large scales, remember on 30 megaparsec scales, say, where things are pretty smooth, the value of delta is 0, and the variance is given by this sigma squared. Okay, good. Let's do it like this. Let me hold off on that for a second, just to come back to this variance, and then I'll come to the question. So so here I said the field is Gaussian on large scales, and I wrote it in terms of the real space thing, right? What I want to do now is make a connection between this stuff, the power spectrum, and the real space fluctuations. So here goes. So imagine taking this variance squared. This is the fourth point. So we defined it on the first blackboard as just delta of x squared. Right? But now we know a lot about this. We can actually do a lot of computations here. So this is equal to, let's do it in terms of Fourier mode. So this is d3k over 2 pi cubed times e to the I k dot x, and then d3k prime over 2 pi cubed times, we take the complex conjugate, e to the minus I k dot x prime. For delta in real space is positive, is real, so the complex conjugate is the same thing as the thing itself, so we can take the complex conjugate. So, and then we're taking delta twiddle of k times delta twiddle star of k prime. And this is, right, that's correct. So does everyone agree that this variance is equal to this thing in Fourier things, right? That's correct. We know what this is. This is 2 pi cubed delta 3 of k minus k prime times the power spectrum. So this k prime integral goes away, right? With k prime just set equal to k, and this is x, because we're taking delta of x everywhere. So what we're left with is d3k times the power spectrum, and then k minus k prime is just 0, right? So what we're left with is the variance. So remember, what the variance is you're looking here and here and here, and just the variance in delta. So that variance is equal to the integral d3k over 2 pi cubed times the power spectrum. And that, by the way, delta is dimensionless. This thing is also dimensionless. K has dimensions of 1 over length. So this thing has dimensions of length cubed. So it's useful to form a dimensionless combination of these things. Do the angular integral, you get a 4 pi, and you're left with a logarithmic integral dk over k times the dimensionless combination k cubed p of k over 2 pi squared. This thing is called capital delta squared of k, and this is the language I want to use to answer your question. So we can plot this thing as a function of k. And this is in units of, k is units of 1 over length, so it's units of 1 over megaparsec. Delta squared is a dimensionless quantity. So that means when delta squared is greater than 1, the field has gone nonlinear. So in other words, in this room, delta squared is way bigger than 1, right? And on scales of this size of this room. And it turns out that it looks something like this. where this this value where the place where it goes nonlinear is about 0.2 or 0.1 or something like that. So on these scales, the field is linear, and it's also pretty Gaussian. And those two things are related, because as long as the field is linear, each Fourier mode, this speaks a little bit to what Caitlin was saying before, although not completely, each Fourier mode evolves independently. So if it starts out as the perturbations were initially Gaussian, they remain Gaussian. There's no mode coupling, right? It's only when it becomes nonlinear that the modes start talking to one another and becomes non-Gaussian. So over here, the field is nonlinear and it's non-Gaussian. Linear means something very specific. It means the delta squared is greater than 1. So what that means specifically is, in other words, this is a dimensionless quantity. Okay, so 1 is the cutoff between linear and nonlinear. So physically, what that means is, imagine putting in a window function. So filtering this field over a top hat filter with a given spherical size. That would correspond to if you convolve something with a filter in real space, you multiply it in Fourier space, right? So that would mean the filter here would just be a window function in K space, right? So imagine putting in a window function in K space where you only pick out this value, this region here. What I'm saying in that case is that the variance would be much bigger than 1. Does that make sense? Whereas if you took out a filter, as I said before, imagine filtering it with 30 megaparsec spheres. So you're filtering it over here, the variance would be much smaller than 1. That's a very precise definition of linear. It's not like my homogeneous and isotropic definitions where I didn't know what I was talking about. This I actually know what I'm talking about. So it's very, very clear, linear and nonlinear. Okay, does that make sense? Okay, the Gaussian and non-Gaussian follow for the precise reason that I mentioned, that if the field is linear and the perturbations were initially Gaussian, then as they evolve, they remain Gaussian because they're not talking to one another, right? Because they're linear, that means there's no. So if you write down the evolution equations, right? If the perturbations are small, you can drop all quadratic terms. When you take the Fourier transform of an equation that's linear in overdensities, you get k just talking to k. No, k is not talking to any other k, right? It's only when you have quadratic terms or nonlinear terms in the evolution equation that different k modes talk to one another. Other questions? Okay, so we spent a long time on this, but if we nothing out, and by the way, so this exact same discussion can carry over to the CMB, same exact thing, right? It's the only difference is a 2D field. So the temperature then, people, I think Nalima did this also, and it's fine. She did it on a whole sphere, so she wrote it in terms of YLM, spherical harmonics, right, or Legendre polynomials, right? But that's actually, and that's the right way to do things. But a more intuitive way to think about it is just to think of those L's, the CLs, as the Fourier transform, right? And that's true on small scales where the sky is basically flat. So then instead of the 3D Fourier transform, you have a 2D Fourier transform. And by the way, this combination here, you've all seen many times then for the CMB. Because what you always see plotted is L squared CL over 2 pi. That's the 2D analog to this thing, right? And that's exactly why it is, because if you calculate the variance of the temperature, what you get is the integral dl over L, L squared CL over 2 pi. So that's precisely why they always plot that thing. Yeah.
So just understand Gaussianity versus non-Gaussianity. So it's very early on, in other words, we can use linear curves.
Yeah.
Then we have each k mode, but they do not create non-Gaussianity later on. But then the non-Gaussianity today should come from the Hopian, a non-linear term that was there already.
That was negligible initially.
Yeah, so non-Gaussianity is not really created from the Gaussian mode. So they are not going to complete that if non-linear circuit goes.
I don't understand the question. Can you say it again?
Let's say in very early on,
Yeah.
we can do the linear probability theory, and then we just expand stuff to linear order.
Okay. You could take to the next linear order, and it would be those terms would be very small.
Right.
Okay.
What I'm saying is that let's say I can put the linear order, and there will be
Right.
I'm saying there will be no gradient generated from the linear.
That's correct. Right.
Then basically they should come from non-linear terms.
Why do you put in those last three words? Because we just agreed not to use those nonlinear terms early on because they're not important. So the non-Gaussianity is generated at late times by the evolution. Yeah. So if you have the linear perturbations as they begin to grow, because there's more people on this side of the room, this side of the room over 13 billion years, they'll all migrate over there. So as the perturbations begin to grow, the second order terms that you were able to neglect early on become important, and those induce non-Gaussianity. However, I think what you might have been hinting at is there are theories in which the primordial perturbations are not purely Gaussian. They could be non-Gaussian. So what you have to do then is quite complicated. You have to disentangle the primordial non-Gaussianity from the non-Gaussianity that's generated by gravity. So that's the complex thing you have to do. Yeah. Other questions? Okay, so let's talk a little bit about the evolution then. I mean, it should be. What we're going to find is that this power spectrum depends on cosmology. It depends on physics. It depends on things like the neutrino mass, the dark energy. It depends on the baryon density. It depends on how much dark matter there is. So this thing is tremendously important. It's the premier way to get at cosmological parameters and therefore to get at physics. Okay, so evolution. It turns out that I think Nalima gave you an introduction to this. You really have to solve the perturbed Einstein equations. We solve the zero-order Einstein equations. So in some ways, it's just a question of putting in the perturbed metric that Nalima gave you and just turning the crank. So let me just show you what it looks like in one situation. So when we're looking at wave numbers k that are much larger than the scale factor times the Hubble rate. In that regime, and then I guess, I guess we're also looking at, okay. So anyway, so then in that case, the equation looks like this. Delta double dot plus 2 maybe AH times delta, maybe just H, 2H delta dot minus 4 pi G rho bar delta is equal to 0. So that's the equation that governs the evolution of these perturbations. Yeah. That is regular time. Just so I know who I'm dealing with, what is your last name and who do you work with? Okay. Okay, good. Thank you. All right, so that I got that right. So why is this restriction important? Okay, the reason why it's important is for the following reason. I don't like this chalk. So here is the scale factor A. I've been using A as a as kind of a time variable. Is that okay with everybody? Okay. So, and I've also been implicitly setting it to 1 today. I hope that's also okay. So the so imagine, and then let's put on this axis the length. So a given wave number, the inverse of that is a wave length. and I haven't said this, but the wave number k we're using corresponds to the co-moving distance. It's conjugate to the co-moving distance. So what does that mean? What does k look like, or k inverse look like on this graph? How does it vary with the scale factor if it's the co-moving wavelength? Nothing, right? So this is just a flat line. So imagine you have k inverse looking like this, right? And then ask yourself the following question: what is the distance that light can travel in a finite time dt? Well, it can travel a distance c times dt. That's the physical distance that light can travel in a finite time dt, right? That's the physical distance. We're dealing with co-moving distances, so if we want to put it on this plot, we have to divide by the scale factor, right? So that is equal to, we can change variables, write this as c dA over a dot, right? That is the physical distance, and now let's lose the c. So that's equal to the logarithmic change in a, in the scale factor, d log a, and then a dot is ah over ah. So the co-moving distance that light can travel in, say, the time it takes the universe to double in size is 1 over ah, right? So this is called the co-moving Hubble radius. So, and that's a very important distance. Why? No, it's not. I'm sorry. It's not the size of the universe, because the universe could be much larger, but it's causality, right? So no information can propagate on distances longer than that, right? That's the key thing. So the universe could be bigger than that, right? But light can't propagate any further distances. And how does this distance, this co-moving radius, scale with time? So the co-moving Hubble radius So that co-moving Hubble radius, remember h today goes as a to the minus 3/2, because it's matter dominated. So this thing scales as a to the 1/2 today, right? So it's increasing with time. And then in the radiation dominated era, h goes as a to the minus 2, right? So this scales as a. So it's a to the 1/2 here, and then it's a there. So it looks something like this. And then it no, not at all. It looks nothing like that. So it looks like this, and then it kind of changes slope like that. Right, so this is 1 over AH. And the key point is that it's only regions in here that are causally connected. So if you think about a given Fourier mode, when it's larger than the Hubble radius, nothing's going to happen to it. Nothing can happen to it because it can't be affected, right? So we say that the mode in that case is outside the horizon. So as long as this is true, the mode is outside the horizon. And that means nothing's going to happen. It's not going to evolve at all. And once this happens, the mode has crossed the horizon, so it's inside the horizon. So that's the reason why this provision is pretty important. What this corresponds to is the mode is within the horizon. So that's when evolution can start happening, right? Before then, nothing happens to the mode. So once the wave number becomes larger than this inverse Hubble radius, this equation is the one we have to solve. This is how the mode evolves. Before then, nothing happens, so we don't really care. We don't really have to write anything complicated down. Okay, so let's solve this equation in three different cases. First, the case of no expansion. If the universe were not expanding, well then h, the Hubble radius, is what? The Hubble rate is what? 0. So we just are left with a simple equation. The second derivative delta minus 4 pi g rho times delta is equal to 0. And we know what the answer to that is. Delta is equal to a times e to the plus square root of 4 pi g rho bar t plus some other constant times e to the minus square root of 4 pi g rho bar t. So there's a decaying mode. That's not that important. And then there's this mode, this growing mode, that is exponential, right? This is gravitational attraction is exponential. And as long as the universe is not expanding, there's more people on this side. On this side, it will happen exponentially quickly. And you actually know what the time scale is without doing any calculation, because you know that this thing here is roughly the Hubble constant. And you know the Hubble constant is roughly 10 billion years. So the time scale for cosmological growth is roughly 10 billion years. Yeah.
Is this delta the same delta?
Same delta, yeah. Same delta. Okay. So that is no expansion. Good question. So we're okay. Good. No, right. Sorry. This is the Fourier transform of that. So I've gotten rid of the twiddles. Sorry about that. Yeah. So there's no k dependence. That is, in this limit that k is much greater than ah, there's no k dependence. Yeah. So that means that good question. Good. Thank you. So that all the k's then, all the k modes evolve the same. Okay. Second example is imagine the universe is dominated by matter only. So there's no dark energy or anything, no radiation. And there's matter-dominated expansion, which is pretty much true for most of the history of the universe, going back to when A was 10 to the minus 4 or so. So if that were true, well, the only thing we have to do is figure out what H is. Remember, rho bar goes as A to the minus 3. So in order to figure out what this equation is, we just have to solve the Friedmann equation to then solve this equation. The Friedmann equation in that case says A dot over A is the square root of 4 pi g, 8 pi g over 3 times rho today, which is rho critical, times A to the minus 3. That's the Friedmann equation today, right? And this thing is just h naught squared. So this is equal to h naught times a to the minus 3/2. So this says, I think it's hard for you guys to see, so let me move over here. So this says that you look at this equation, dA, and then there is an a to the minus 3/2 here. So if I multiply that, I get an a to the plus 1/2. Is that right? A to the 1/2 is equal to h naught dt. Do you agree? So that means that a to the 3/2 to the 2/3 power is equal to h naught t. So that means that a goes as t to the 2/3 power. Since a is normalized to be 1 today, that means that a is just equal to t over t naught to the 2/3 power. So that's the simple solution in the case of a matter-dominated universe. Questions? Okay, since that's true, we can immediately calculate the Hubble rate, which is a dot over a. When you take a dot, you just get 2/3 over t. And so this is just equal to 2 over 3t. So what that means is we can immediately reduce that second-order differential equation. It's delta double dot plus twice h. Twice h is 4 over 3t times delta dot. And then it's minus. So this thing here is 4 pi g 3 rho bar delta but let me just write this out. 4 pi g rho bar delta is equal to 0. But this thing is equal to 3/2 times 8 pi g rho bar over 3, which is h squared. Right? So this thing, and h squared we already calculated, so this thing is equal to 3/2 times 2/3 squared is 2/3, 2 over 3 t squared. So that's the differential equation. We have a differential equation in terms of t, in terms of delta, in terms of t, delta double dot, plus 4 over 3t delta dot. And then it's this. This is a trivial differential equation to solve because the powers of t all line up. And so you just assume a solution of the form delta is equal to t to some power. So this first term becomes p times p minus 1. And then it's delta over t squared. And this thing gives plus 4 over 3 t squared times p. I guess there's another delta. And then it's minus 2 over 3 t squared times delta equals 0. So the delta over t squareds go away, and we're just left with a polynomial equation, which is p squared minus 1 plus 4/3, I think, is plus 1/3, minus 2/3 is equal to 0. So the quadratic equation tells us that p is equal to minus 1/6, right? Plus or minus 1/2, the square root of b squared, which is 1/9, minus a minus, which is plus 4, which is 8/3. Do you agree? 8/3, if you multiply top and bottom by 3, is 24/9. 24/9 plus 1/9 is 25/9. The square root of that is 5/3. Right? So this is equal to minus 1/6 plus or minus 5/6. So again, there are two solutions. There's a decaying mode and a growing mode. So the decaying mode has the minus sign, and it corresponds to the overdensities falling off with time, delta going as t to the minus 1. That's the decaying mode. And then there's a growing mode, which is the one we're interested in. Instead of being exponential, the expansion has modulated that so that now it's a power law growth. And the power law grows, delta grows, as delta goes as t. 5/6 minus 1/6 is 4/6, which is 2/3. T to the 2/3, which is proportional to the scale factor. So the overdensities grow as the scale factor.
So why do you jump from no expansion to matter domination? Why don't you do the radiation domination?
Because it turns out in radiation domination there's almost no growth. Delta remains roughly constant. Good question. Other questions? Right. Good. Well, it's the same thing, right? I started with this equation, so that's what it is. Yeah. So at these in this limit where k is much bigger than ah, it turns out that it doesn't depend on the let's not call it momentum. Let's call it the wave number. No wave number dependence. Yeah.
So
Yeah. Sorry, go ahead. What saturates it? Nothing. In fact, it's just the opposite. This is linear. I should have said at the beginning, this is the linear evolution. When Matthias comes, maybe he'll talk about nonlinear evolution. But in fact, what happens is, as you include the nonlinear things, look at the density in this room. Right? So how did it get to be 10 to the 30th bigger? It didn't saturate, it accelerated. So when things become nonlinear, they go haywire. So it's just the opposite. Right? And there's actually... Okay, anyway. So you had a question?
No, I
Okay.
forgot my question.
Okay. That's all right. Other questions? Okay, so that's interesting. The expansion changes the power law growth to a polynomial growth. It makes sense, right? The universe is expanding So it's harder for matter to accrete more matter, right? In fact, there's another way of thinking about this using Poisson's equation. Remember, Poisson's equation is del squared phi is equal to minus. Let me write it for real. So in terms of the Fourier modes we've been looking at, it's k squared phi is equal to 4 pi g rho bar a squared delta, and I guess there's a minus sign, although people's convention on phi vary. So, and this is again with, just to be explicit, this is with these Fourier modes. So look what happens here. When in this example, when delta scales as the scale factor, grows as the scale factor, this combination gives you a cubed. The matter density falls off as a to the minus 3, which means the gravitational potential is constant. And so that is a quite beautiful way of resolving this apparent conflict. What happens to gravitational potential wells as the universe expands? On the one hand, the universe is expanding, drawing matter further away, so you'd think they'd become less deep. On the other hand, gravity tends to accrete, so matter falls in, so it tends to make it more deep. And the answer is it's a tie. They remain exactly balanced, right? And what that implies is that if you have something that breaks the tie, even if it's small, it's gonna lead to important ramifications.
So which is like when the potential remains constant.
Good. It's at late times when the universe is matter dominated, right? So, but that leads to the first time when the tie is broken, the first thing that breaks the tie, and that is dark energy. So dark energy does not participate in this clumping, and that means that the phi is going to decay when dark energy becomes relevant. Remember I said dark energy becomes relevant only at very recent times, when A is greater than a half or so. So if you would plot, say, so people tend to talk about this the growth function. Is there a what? The time. Well, this is intuitive way. That's a good question. I'm not sure. I mean, there should be, right? We should be able to figure out an intuitive way to think about it. I don't know. That's a good question.
Sorry, by the way, in that equation, why we don't see any effect of gravity? It's independent of the way better production works. It's already massaged in the sense.
No, it's in gravity. There's a G here. If you turn off gravity, it goes away. Right. I mean, look at this thing. Look at the initial. That's a good reason for doing the no expansion case first. If G is equal to 0, the time scale is infinite. There's no growth. As G goes to 0, the time scale is infinite. That's 1 over the inverse time scale.
Sorry, I might have missed something, but is that equation, did we derive that, or is that?
Oh, no. But Nalima wrote a lot of stuff, and we did a lot of stuff last time. So if you take those two pieces of stuff and spend a week, you'll get there. Yeah. Okay, so I just want to make this point about the growth function. I said it is this tie, and someone said, when does this apply? And so one thing that breaks the tie is dark energy. So it turns out that dark energy, you just solve this exact equation. But the only thing you have to change is, remember, in order to solve this equation and get this that the growth factor goes as the scale factor, things grow as the scale factor, we had to use this solution to the Friedmann equation, right? That's no longer true if dark energy dominates, because dark energy doesn't fall off as a to the minus 3, right? So that solution we got up there is wrong. So you just have to rederive the solution. It actually is an analytic thing, but you can just do it numerically, solve the Friedmann equation in presence of dark energy, and plug it into that differential equation. And what you find is the following. As a function of, again, A. So here's 10 to the minus 1. Here's 1. So the growth function is defined to be D delta over, say, delta initial. So remember, as at early times, it's just going up as it's going as the scale factor. So it's just linear in the scale factor. So if the universe were matter dominated, it would just look like this. But because of dark energy, at early times, dark energy is not that important. But as you get to Z of about a half or A of about a half, whatever, the dark energy becomes important and growth stops a little bit. So in the presence of, say, a cosmological constant, you have a growth factor which is suppressed by about 20%. And that makes sense, right? Because it's breaking the tie, so because it's not clustering, and that means that the gravitational potential wells are going to decay, and that's going to lead to less growth. And that's important, because what that tells us is if we can measure this growth function by measuring how structure evolves in time. Remember, that's a complicated thing, because what we have to do is measure something, for example, like the variance as a function of time, right, to see how it evolves in time. We can't just measure one thing, because that doesn't count in cosmology. You have to measure statistics, right? So you have to measure this variance or the power spectrum as a function of time, and if you can do that, then you can eke out information about the dark energy. Does that make sense? Okay. Other questions? I? Initial. Sorry. That's not true, is it? Because that would be 1 then. So that's I don't know what this is. This is some D is a constant times delta, where the constant is to be determined. Okay. I mean, in this case, I've normalized it. This is relatively important. I've normalized it so that it scales as A early on, right? And more precisely, we have very accurate measurements of the clumping at the CMB epoch when A was 10 to the minus 3. So that might make the most sense, the place to normalize this thing. And then it scales as A all the way up to the dark energy epoch, and then whatever. Some people normalize it so that it's 1 today, which would mean that the growth function for lambda CDM, for example, would be larger at early times. So it depends how you normalize things, right? Other questions? Good. So remember, H is today is 1 over H is 3,000 megaparsecs. So when that's anything that we can measure, and remember the action is around k of about 0.1, which is much smaller. It's k of about 1,000 times h naught. So roughly speaking, the stuff we're measuring today is 100 to 1,000 times h naught. So all of you have touched on the point that until now we haven't talked about anything that depends on k. So next time we'll talk about something that does break the tie in a different way than dark energy, in a k-dependent way, so we can learn about that thing by measuring the k-dependence of the power spectrum. And then we'll move on to different probes. Okay. So there's photos now, you said?